Now, we just got done looking at the easiest type. There we go. But this is when we don't have the easiest type. It's called the steady state approximation. This is when you have a mechanism with a fast initial step, okay? Or I could say conversely, not a slow initial step. The rate limiting step may contain intermediates, so things that don't technically exist in the reactants or products. When you got the previous step is fast, reaches equilibrium, so that's the double arrows. We haven't got into that till unit 6, but it should be something that you'd seen in your past. The forward and reverse reaction rates are equal, so the concentrations are related and the product is an intermediate. We substitute that into the rate law of the rate determining step. This will produce a rate law in terms of just reactants. We can't have it with intermediates in them, so we'll rearrange, substitute it to write it without them. So not so fun game of substitution. Now, keep in mind for each elementary step, the coefficient equals the orders. So let's look at the first one, right? So we have the fast rate here. So that would be NO squared, okay? NO squared is going to be equal to the other K to the first. When we have this double arrow, also sometimes written as like two arrows like this, that means they're equal, but opposite. And the opposite component is going to be this K negative 1 and K1. So what I can do is if I'm solving for the intermediate N2O2, I'll see that that's the rates over equal to NO2 squared. Now I can tell that this one is my slowest rate. So my slowest rate is going to be, again, the coefficients from our problem. So 1, orders 1. N2O2 is going to be 1. Now, I substitute, now I found out what N2O2 is, I substitute it in. So when I substitute that in, I'm going to get H2, which is fine there, and NO2 squared, the NO2 squared comes here. Now, as far as your rate, the actual rate component, you might be asked to determine what is like the ratio between these two here. Again, you're going to plug them in, right? If I plugged it in here, I'd have K2 times K1 on top, K negative 1 on the bottom. This to the first order, this to the second order. This K prime is essentially what this is. Sometimes that'll be referenced as K prime. Sometimes you'll need to be able to tell us what is the order of these different rate constants. It all depends on the question. But what we do, again, just to kind of summarize, we use the slow rate to determine the basic rate law for that slow rate. I see it has a intermediate in it. I need to substitute that out from what the intermediate is from something that's from the reactants. I did that here. So therefore, I'm able to plug that in and get my overall observed rate law. Now, if that was too fast, like the first step, let's look at another. So this one I mentioned, I think a couple times before. So looking at this, what's the overall reaction? We need to add these all up, identify the intermediates in the mechanism, what's the predicted rate law? So let's look at it one thing at a time. Overall reaction, I have to add things up, cancel things that are the same on both sides. I say I have two chlorine atoms, CCl3, CCl3, and so I add things up in order to get my overall reaction. Intermediates are things that are generated in one place, used up in another. So that's Cl as an atom, and CCl3. Now, because the second step's the rate determining step, the one in the middle here, I would originally start off with one of these and one of these, because that has a coefficient of 1 and 1. But because Cl is an intermediate, I can't have that there. So I need to take something and solve for it in reverse. So I see the original that these two are equal because they're at equilibrium. That means they have equal rate of reaction. And so when I solve for Cl as an atom, I get this. Substituting it into the first rate expression, I substitute it in. I get Cl to the 1/2, a new K. This time I didn't take it of what those each would be, but simplifying the reaction, I get K Cl to the 1/2, which is kind of rare, but easily doable as you see, and CHCl3 to the first order. So this order of the rate of the reaction would be 1.5. All right. Come in with your questions. Again, these are the hardest, but they're still very systematic. So try to see a pattern for it and go through it as is. Let me know what kind of questions you have. Catch you on the flip side.